following sequences. Can you guess how the terms of these sequences are progressing? Let us observe these sequences closely. We observe that each successive term in the first sequence after the first term is related to its previous term as shown. Similarly, each successive term in the second sequence after the first term is related to its previous term as shown. In the same way, each successive term in the third sequence after the first term is related to its previous term as shown. Hence, it is observed that in each case, the ratio of each term with its preceding term is always constant, except the first term. The constant ratio observed in all these sequences is generally known as common ratio. Observe that in the first sequence, the common ratio between the successive terms after the first term is 3. In the second sequence, the common ratio is 1/2. In the third sequence, the common ratio is 0.1. All the above sequences are known as geometric sequences or geometric progression, in short, GP. We will now define the geometric progression as a sequence of non-zero numbers a1, a2, a3 up to an, such that the ratio of each term and the term preceding to it is always constant and is given by as shown. Consider the given example. Let us consider a GP with first term A and common ratio R. Consider its first few terms. Observe the pattern followed one by one. In the first term, the exponent is 0. Observe the relation of the exponent with its position. In the second term, the exponent is 1. Observe the relation of the exponent with its position. Similarly, observe the exponent of the third and the fourth terms with respect to their positions. Based on this observation, can you find the 12th term? The 12th term can be given by the following expression based on the observed pattern. Therefore, the pattern suggests that the general or nth term is given by the following expression. Based on the number of terms and the definition of the general term, we can write a finite GP in the following way. The series associated with the above sequence is called finite geometric series. Similarly, an infinite GP can be written in the following ways. The series associated with this sequence is called infinite geometric series.
Let us now find out the terms an and a5 for the GP given here. Here we see that the first term is equal to 0.15 and common ratio is equal to 0.1. The term an is given as shown here. Putting n is equal to 5 in the above formula, the value of term a5 can be calculated as shown here. Let us find the correct answer for the given question. Here the first term of GP is 5 and the common ratio is 2. Let 5120 be the nth term of the GP. Using the general term formula, we get the value of n as 11. Hence, 11th term of the given sequence is 5120. Now we will try to find the sum to n terms of a GP.
Let us now find the sum of the first n terms of a GP. Let the first term of a GP is A and the common ratio be R. The sum of the first n terms of such GP is denoted by Sn and is given by the following expression. Here, we will consider two cases. Case 1. If R is equal to 1, we have the sum to n terms of the GP as shown. Case 2. When R is not equal to 1. In this case, multiply the equation 1 by R. We get the following expression. Now, on subtracting the equation 2 from the equation 1, we get the following expression, which on simplifying gives the value of the sum to first n terms of the GP as shown.
Let us now find the sum of the 10 terms of the GP, 5, 15, 45, and so on. Note that the first term of the given GP is 5 and the common ratio is 3. We have to find the sum of 10 terms of the above GP. Using the sum formula for GP, the required sum can be calculated as shown here.
Now, we will find the sum of the infinite terms of a GP. Consider a geometric progression with first term A and the common ratio R. Consider the sum of its infinite terms. It is denoted by S infinity and given by the following expression, such that the numerical value of R is less than 1. Note, if the numerical value of R is greater than or equal to 1, the sum to infinite terms of the GP tends to infinity.